Hey, PSTAT students, Mr. Mitchell here. Today we're going to look at hypothesis testing, a new concept for us. We're going to take a look at hypothesis testing with proportions today. We're kind of looking at two things at the same time. Go ahead and share my screen with you. If you want to pull up in Schoology worksheet 9.1, 9.2, we're going to take a look at this example here. We're going to go through the whole process of what hypothesis testing is, take a look at a couple things in our notes. Don't forget, you do have notes that you do want to read through. It really explains a lot of other things so that we can't necessarily go into great detail in a video because it would be very, very long, but it does go, they are really, really good. So Leroy, a starting player for a major college basketball team, made only 40% of his free throws last season. During the summer, he worked on developing a softer shot in hopes of improving his free throw accuracy. In his first 8 games of the season, Leroy made 25 free throws in 40 attempts. You want to investigate whether Leroy's work over the summer will result in a higher proportion of free throw successes this season. Okay, so if we want to discover why hypothesis testing and maybe not a confidence interval, well, we have something that Leroy did before. Okay, he's a 40% shooter. This isn't like when we have an election, like a presidential election, and we're trying to figure out who's going to win beforehand, because we have no idea who is really going to vote for whom. So we need, in that case, we don't have anything to go off of except for other polls. But with this, we do have something that is known to be true. This was a fact. He's a 40% shooter. But we're trying to see whether the work he did over the summer has improved it. Okay, so that's really what leads it that we're doing hypothesis testing. We have something that was known to be true, but now this happened. It makes us think that this might not be true. Okay, example would be the Earth. At one point, everybody knew that it was flat. Wasn't a real argument, 1,000 years ago or whenever it was. Everybody thought the Earth was flat. Okay. And then there's some evidence started to come around. People started to, maybe it's not flat because of X, Y, and Z. So that's kind of the same type of thing. This is true. Can't really dispute it. At least it was true. Okay. But now we're wondering if it's not true. Okay. So what we want to think about is this is our P, and then these two things make up our P hat. So P hat is really 25 over 40, okay, which is what, 60 some percent? 62%. So it's 0.625. Okay. And then our P is just 0.4. So you can see that is definitely an increase, right? That's 22.5% increase. So that's pretty big change if he has in fact improved, or is he just getting lucky and by random chance that this has happened? Okay, so that's kind of the thing that we're looking at. Can this improvement with this many shots, is this just by chance? Is he going to start shooting worse over the next 6 games, 10 games, whatever, and is he going to be back down in the 40%? So that's kind of what we're doing. So let's take a look. The hypothesis testing is 4 steps. And it's really similar to confidence intervals. It is a little different. So identify the population and parameter of interest. So we are looking, our population, we are looking at Leroy's free throw shooting percentage. Okay, that's really what we're looking at. And we're looking at P. P is equal to the proportion of free throws made. Okay, so that's identify the population and parameter of interest. This is what we're looking at. And then state the null. The null hypothesis is known truth. The alternative is new thoughts. Okay. So you don't have to write this on every single problem, but that's what a null hypothesis is. If that's the first time you're hearing it, that is what is known to be true. The alternative is what we're thinking, ooh, maybe that's not actually, maybe this known truth isn't true because we have new thoughts. We have new things that are happening that make us believe that it's not. Okay. So our null hypothesis, we write that as H naught. Okay. So that's the null hypothesis. So we write it in symbols. So the proportion, what was known to be true? Known truth is that it's 0.4. And then we need to write that out in words. Okay. Can't just write it in symbols. This is in symbols. That's our null hypothesis. So Leroy's free throw proportion of makes is 0.4. Okay, so that's what Leroy does. That's what he's been doing. So now we have alternative thoughts. So we label that as H sub A. So what's our alternative thought? We don't ever use p hat. We never use a statistic in here. It's always got to be a parameter in our hypotheses. So look at the proportion, the sample proportion. What are we proposing? Are we proposing that it's, because it's got to be one of three things. It's either going to be greater than, less than, or not equal to for the alternative hypothesis. So what are we proposing here? We're proposing that he's gotten better. If we were proposing he's gotten worse, then it would be less than. If we were proposing it was just different, like it could be better or worse, it's just different, then that would be not equal to. But we're proposing that it's bigger than 0.4. We're not saying that it's 62.5% or 0.625. We're just saying that it's larger than this number. Okay, how much larger? We're not going to make that claim. We're just going to say that it's larger. It's better. It's bigger than 0.4. So then in words, Leroy's free throw proportion of makes is larger than 0.4. So again, you just write this out in context, right? We're talking about Leroy's free throw shooting percentage, his proportions made. Okay. So I need to have it in symbols and then I need to have it in words. And you never use p hat. You always use p. Right? Even though we will find p hat, we use p hat, but not in our hypotheses. So identify my population, I identify my parameter of interest, and then I need to state my null and alternative hypothesis. This is step one in our process. It's a little bit longer for hypothesis testing for step one than it is for confidence intervals, but it's still the same type of thing. Yes, it is different. It has some different things in it, but it's still the same thing. What are we doing? With a confidence interval, we were estimating blah, 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 blah. Now I got to identify the population parameter of interest. And you can get these two things into one sentence if you like, just like we did with confidence intervals. Then we do need to state our hypotheses should be a null. Again, that's the known truth, what was known to be true, at least for right now. We could have evidence to show otherwise, to try to prove otherwise. Okay. So that's step one. So now we got to go to step two, which is the same thing that we did with confidence intervals. So what kind of test are we running? So we're performing a significance test. So what are we doing? Well, we're dealing with proportions. We're doing a one sample, right? There's only one sample here. Leroy has one sample this season that we're looking at, 25 out of 40. So one sample Z test. All right, we're doing a hypothesis test. It's not an interval. One sample Z test for proportions. Okay, so we always got to state what tests we're going to run. All right, so now we have our checks. So we need an SRS. So it's not really random. It's kind of iffy on that. But we're going to assume an SRS, and that's real iffy. Okay. In this problem anyway. All right. And in other problems, it's going to tell you that it's random. I don't really think that it's a simple random sample because I'm pretty sure it's all of his shot attempts. So that's not really random. So that it could be iffy. We're going to put it in there. We're going to assume that it's an SRS, but it's probably not really. But we're trying to learn how to do this process. Typically on the AP test, they're not going to give you a problem that doesn't pass the checks. So we just got to be careful with that. It's probably not an SRS. We probably wouldn't be able to continue, but we're going to continue just so we can learn how to do this. So now we have our population being greater than or equal to 10 times the sample size. So I don't know how many he's going to shoot. Do you think he shoots more than 400 in the season or 400 in his career? I think that's probably a safe assumption. So Leroy shoots more than 400 shots. I guess I should be more specific than shots. That should be free throws. Okay. If that's not true, then we violate the independent condition, the replacement versus non-replacement, and we would have to cease and desist. Okay, so we are making some assumptions here just to continue. We have looked at this question before in other situations. So we're just trying to piggyback off of something that we've done before. Okay, so that's another check that we need. It's kind of an assumption again. Yeah, I don't know how many free throws he would make. I think if we're looking at like LeBron James or really good basketball players, they shoot a lot of free throws during games. So it's probably okay that we're assuming that he's going to shoot more than 400. Okay. But look at it. What are we talking? Major college basketball. So if you think about like Duke or Connecticut or one of those teams, they play what? Almost 40 games in a season. It's not unheard of to shoot that many. So we've got to assume that. So then our approximately normal or large counts, we have to check n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. And we are actually going to use p. We've talked before about confidence intervals. When we don't know p, we use p hat. Well, we know p. P is 0.4. We couldn't do hypothesis testing if we don't have an actual population proportion. Okay, we would just be doing a confidence interval then. So we're going to take n, which is 40 times 0.4, and that's got to be greater than or equal to 10. And then we're going to take 40 times 0.6, and that's got to be greater than or equal to 10. I should have gave myself some more space here, but I didn't. So what is 40 times 0.4? I believe that is 16. So I think we're good there. And then 40 times 0.6, what's that? 24. And that's greater than or equal to 10. So I think we are approximately normal. So I think we meet all of our checks. Okay. Or at least we have to assume. Okay. If this were the real world, we may be a little hesitant to continue, but we're just trying to learn and practice. So now we're going to calculate the test statistic and the p-value. Okay. So we're going to do it first by hand, then we'll use the calculator. So we are finding really a z-score. Remember x minus mu over sigma. It's really in the same format, but now we're going to find p hat minus p over the square root of p times 1 minus p over n. So p hat is 0.625 and p is 0.4, right? We already found these two above. And then we're going to put in 0.4 times 0.6, number 1 minus p. So these two have to add to 1. And then that's divided by 40. Okay. So using my calculator, 6.25 minus 0.4 divided by the square root of 0.4 times 0.6 divided by 40. 2.90 is what I got. Okay. Hopefully that is correct. All right. I'll just type it in one more time just to verify. Yep. So we're good. All right. So this is my test statistic. Okay. So they want the test statistic. That's this. P-value. So we found those before. We just didn't call them a test statistic. So everything we're doing, we have actually done before. We just called it something different. You don't call it a test statistic. You don't call it a p-value unless you have hypotheses with it. So we're going to call it a p-value. It's really just the probability that we found before using z-scores or normal CDF. Okay. So it's really the same thing, except for it has context. The context is we're doing hypothesis testing. So now we need to find the p-value. We could do normal CDF, but since we're doing it all by hand, I am going to go use the table. So let me pull up my table here. So I need to find 2.9. Here's 2.9. So 0.9981. Now remember, when you use the table, you have to do 1 minus that if you're going to do greater than, if you want to the right. So I look that number up. So 0.9981. So I got to do 1 minus 0.9981, and I'm going to get 0.0019. There's my p-value. Again, it's only called a p-value when you have hypotheses with it. If this is the problem all by itself, it is not called a p-value. It's called a probability. This is just called a z-score or a z-statistic. Okay. So this is the work that we do. And so now let's take a look at our calculator. If it lets me load it up. Okay, I'm back. Hopefully had some technical difficulties here with getting the calculator pulled up. So once we have our calculator, again, we're just doing the same thing we did by hand, but just with a calculator. So anytime you want to run a test, you go to stat tests. So now what kind of a test are we running? We're doing something with a proportion. So we have to find the proportion option. So here's 5, 6, A, and B are really your options for proportions, if you will. You have a proportion, Z int, but we're doing a test, okay? And we're doing a 1 sample Z test for proportion. So that's number 5. So I'm going to select that. And so P naught is just P. I don't know why they have it as P naught. That's just the way our calculator does it. But our P is our proportion, our known true proportion is 0.4. He was a 40% shooter before. Well, now what's the new information? Well, he made 25 out of 40 shots. Okay, so I want to put those numbers in there. You cannot put decimals in here. It will give you an error message. You have to put in the whole numbers of raw numbers made or raw number of successes out of however many are in the sample size. Okay, so if they give you a percentage for p hat, you do have to convert that times the number. So then now we have to select our alternative hypothesis. So here's not equal to, here's less than, here's greater than. So we want to do a greater than, and then we're going to calculate it. There's the Z statistic we found. Yes, it goes more decimal places on the calculator. And then there's your p-value. It doesn't call it a p-value on our calculator. So you do need to know what to look for on the calculator. It also gives you p hat and n here. All right. So if you are doing this with a calculator, you do need to say what type of a test you're running, like what's the option that you're using on the calculator. And then you need to say you got this number, and these are the numbers that you use to find that. And that's okay. They're more interested in the process than they are just in the final answer. Okay, just as with confidence intervals, getting step 3 right only isn't going to get you a whole lot of points. You have to get all the other stuff correct. Okay, so now it's time to draw our conclusion. So we had the Penn State conclusion when we do the confidence intervals. It's a little different here. We've talked about this type of conclusion before. So we're going to compare our p-value to our alpha level. So sometimes they don't give you an alpha level when you get to choose. Well, you either choose 0.01 or 0.05. and you just state it. Okay. So since our p-value of 0.0019 is less than our alpha value of 0.01, we reject the null hypothesis. And then I'm going to state my hypothesis, H naught, that P equals 0.4. Okay, so what we're trying to do, we're comparing our p-value to our alpha. So if this is smaller than that, remember we talked before about probability. Remember we said if it's less than 0.05, then something special is happening. This is what we were leading up to now. Okay, we've been talking about that every time we looked at probability. Now that time frame that we talked about before, it's finally here. So since our p-value of 0.0019 is less than our alpha value of 0.01, we reject the null hypothesis, H naught, P equals 0.4, and have evidence. We're not proving anything. We have evidence to support the alternative. Let me give myself some more space here. We have evidence to support the alternative hypothesis. HAP is greater than 0.4. We have evidence to support the alternative hypothesis. HA is greater than 0.4. That Leroy, now here's where we get our context. Really, this is very general, right? I can't just stay general. At some point, you can put context in sooner. You can put it in the middle. You can put it at the end. To me, I like to stay general and then get specific. That's just my preference. I have to have my context in there somewhere there. You're going to lose a lot of points. That Leroy's free throw shooting proportion has increased to more than 0.4 after working in the summer. Forget whether they said summer or off season. Maybe I should go look at that real quick. Or the summer. So I was correct. It was summer. Off season, I think that would have been okay. They're just, again, what are we looking for? Where are the bullet points that they're going to look for? Did you state your p-value? Did you state and compare it with the alpha level? If they don't give you an alpha level, I would state 1. You don't have to state 1 as long as you say that it's smaller than any alpha level that you would choose. Okay. So state your p-value, compare it with the alpha. All right. You want to link it to the alpha level, and then you got to draw the right conclusion from that. So if the p-value is greater than the alpha value, you fail to reject. We're going to talk about that here in a second, looking at some notes. All right. So they're looking for the linkage. Did you make the right decision then? So if the p-value is very, very small, then we're going to reject the null. We have evidence to reject the null, and we have evidence to support the alternative hypothesis. And then do you have the context? So those are really the 4 things that they're looking for to get this step 4 correct. Okay, because again, this is step 4 in our process. It's number 4 here on this problem. It's step 4. It's still the same type of conclusion that you're drawing, whether you're doing a confidence interval or hypothesis testing. Okay. All right, so now they usually ask some follow-up questions to go along with this. What would a type 1 error be in this situation, and what would your probability type 1 error be? Okay, so we need to take a look. Again, there's a lot of good notes here. So the one thing we want to talk about is comparing whether we reject the null or fail to reject. We never accept the null, never accept it. Okay. Again, thinking about the earth as being flat, we can use that example, or we can use this example of a jury. If they say you're guilty, you reject the null. So you're presumed that you're innocent until proven guilty in the United States. Okay. In other countries, it may be different, but in our country, you're presumed innocent until proven guilty. So if you're guilty, you are rejecting the null. Okay. Because it's known to be true that you're innocent until the district attorney can prove that you're guilty. So if you're not guilty, you fail to reject the null. Not guilty does not mean that you're innocent. It just means there wasn't enough evidence to convict you. Again, a not guilty verdict does not guarantee that the defendant is innocent. Okay. So you can be found not guilty and have committed the crime. Some people are guilty, but because the police did something wrong in collecting the evidence, or certain paperwork isn't filed the right way, or a witness goes missing or changes their testimony or whatever, they still could be guilty, but they couldn't prove it. So then they're not guilty. They're not innocent. Innocent means they definitely didn't do it. Okay. So we want to make sure that we are keeping that in mind as we're kind of drawing our conclusions and everything. Okay. But getting on the type 1 and type 2 error, the different types of mistakes that can be made. Okay. So again, read through those notes. They are very important, but here's what we want to talk about. We're going to talk about type 1 and type 2 error. We're only going to talk about finding the probability of type 1 error. Type 2 error comes later. Okay. So the definitions. So if we reject the null when the null is true, we have committed type 1 error. So we reject the null when the null is true. So we reject that they're innocent, find them guilty when they are actually innocent. That's type 1 error. Type 2, when we fail to reject the null, when the alternative is true, we've committed type 2 error. Okay, so the best way I can think about doing this is talking about it in terms of medical terms. So we're deep into this coronavirus, and some people get a test and it says that they have the coronavirus, but they don't. Okay. Well, what is that? And then we have other people that get a test and it says that they don't have it, but they do. Neither situation is good. Okay. One could be worse than the other, but those are type 1 and type 2 errors. Okay. So we reject the null when the null is true. We've committed type 1 error. If we fail to reject the null when the alternative is true, we've committed type 2. Okay. So it's a false positive, false negative. Okay. So we want to think of it in terms of that. So here's this little box down here that can help us maybe figure that out. But again, I think more using it in type 1, type 2, comparing it to false positive, false negative. So a false positive is when we say that you are sick, but you're not. That's type 1 error. Okay. False positive says, oh, you have the coronavirus, but you don't. You're healthy. It's false positive. That's type 1 error. Okay. We rejected the null. We rejected that you were healthy and said that you were sick, but you were actually healthy. Type 1 error. Okay. And then the other is a false negative. We fail to reject the null. We say that you are healthy, but you're not. You do have the virus. That's type 2 error. Okay. So in some cases, one can be worse than the other. If you have to guess which one's worse, usually type 2, is worse, but not all the time. There are cases where you could consider the other way. So if they say you have the coronavirus, but you don't, what do you have to do? Well, you have to quarantine. So you're out of work or off school for 14 or 10 days, whatever it is now, but nothing else really happens. So that's not great. Neither error is good, but they both can happen. Type 2 is they say you're healthy, but you're not. That's probably worse because then you're going to get other people infected and you're not getting maybe treatment for it. Okay. So let's go back to our problem here. What would type 1 error be in this situation? And what would your probability of type 1 error be? Okay. So type 1 error would be saying that it's a false positive. So It's saying that, let's go back to our hypotheses. It's saying that we reject this when it's true. So type 1 error would be saying we conclude Leroy's free throws proportion shooting, I guess this is in great English, shooting free throws proportion shooting has improved when it actually has not. When we say it improved, it got greater than 0.4 when it's still equal to 0.4. Okay, putting it in context. Okay, so the probability of type 1 error is always equal to your alpha level. So whatever alpha level you use in your problem is type 1 error. Okay, because that's the level that made you decide to reject the null. Okay, remember we compared our null hypothesis with the alpha. We compared our p-value to the actual alpha level. So if our p-value is smaller than the alpha, which it is here, we're going to reject. So this is the value that made us go with the alternative hypothesis. So we got to put it in context. Think of it as a false positive or false negative. Okay, false negative. Type 2 error in this situation would be concluding that his free throw shooting percentage is still 0.4 when it actually has improved over and it is more than 0.4. Okay, the probability of that is a more complex calculation, and we'll get to that later. Okay, we're not going to do that right now. So we could also construct and interpret a 90% confidence interval for the proportion of free throws Leroy will make this season. And then we can use that to work with hypotheses. We're going to work on that at a later time. I don't want to do that right here at this moment. Okay. Just want us to try to wrap our heads around what hypothesis testing is, the 4-step process, and then trying to make right decisions using correct terminology. Okay. So let me know if you have any questions. We're going to take a look at a lot of this stuff in class and work on these types of things. Okay.